Physicality. Muscle fiber typing. Any muscle fiber types? From our perspective, we're going to stick with fast and slow. Okay? In true actuality, there's a big gray area. Okay? So, but again, from our perspective, really it's easier to keep it simple with just a type 1 and a type 2, or a fast twitch and a slow twitch. But understand, again, if you go to graduate school, if you're anything that's related to muscle, they will talk about a lot of different types. And the types, again, when we get to a single muscle fiber and how we quantify what is a type 1 and a type 2 really gets pretty complicated. So I always try to include that so down the road you're not like, he told us there's only 2 types. Well, again, from our perspective and what we need to know about movement, that's pretty good. That'll suffice. But there's a big gray area between kind of these extremes of fast and slow. Okay, so fast twitch. When we talk about a fast twitch, this is going to have a high capability for the electrochemical action potential. What does that mean? What just about this part though? What's happening in the electrochemical transmission of the action potential? How would you describe that?
Quickly.
Say it again.
It's happening really fast. to your body.
What's happening really fast? Both right. Just what's happening really fast.
The muscles are being contracted quickly.
Why?
Because
Why? What's the action potential? Say it again.
I said a graded potential.
What is it though?
like what's going to happen.
What is the electrical chemical transmission?
There's a difference between the salt concentrations.
Okay? That's real specific. What is it in general? What causes the muscle to contract? Nah. What happens if I want this muscle to contract? What do I have to do?
Oh, it's the it's the sign that's sent to your brain. It's like the signal.
Okay. Signal from the brain to the muscle. So the nervous system, right? That's fast. Okay? That's what I'm saying about it's fast and contracts fast. When I say it inside my skull, it gets to the muscle fast. Okay? That's the action potential. So it has, in a fast twitch fiber, it has a high capability of that. Okay? Myosin ATP ACE. What does ACE mean? Medical terminology. Okay, it's an enzyme and it's going to split. Okay? So it's splitting ATP. What happens as a result of splitting ATP? Energy is released. So it has high activity of that enzyme. Okay? We mentioned calcium. Calcium is going to be released and taken back up quickly. Again, we'll talk more about the process, but that's one of the characteristics of the fast twitch. Cross-bridge cycling, that's the connection between actin and myosin, the release, moving to the next one. That's cross-bridge cycling. It does that quickly. How much faster than a type 1? About 3 to 5 times. What sorts of activities would it be beneficial to have a high percentage of fast twitch fibers? Sprinting. What else? Jinx, you owe me a Coke. Sprinting. Sorry, I missed it.
Oh, I said like swimming, like sprint.
Swimming, a sprint. Okay. What else? Weightlifting. All right. Anything that's powerful, explosive. A maximal exertion. All right. So jumping. So we're looking at maximal exercise. Again, so We're not talking about jogging, right? We're not talking about long distance swimming. We're talking about sprinting, long jumping, then lifting, right? And also stop and go activities. Okay? So to start and to stop. We'll talk a little bit more about this when we talk about maturation. But one of the things that happens as people ages is we convert our fast twitch muscle fibers to slow twitch muscle fibers. Why? Because we're not doing a lot of this stuff, right? If we're not moving maximally, we're not sprinting, we're not jumping, why take care of those, right? So we'll convert them to slow twitch. So what might an elderly person have trouble with? What kind of example are you thinking of? It's not I don't know, again, it's not like, and we're going to talk about reflexes, it's not like this reflex, right? It's not that kind of reflex. But more types of agility types of movements. Yeah, so it would be, I'm walking down the stairs and I stumble. Fast twitch is going to get me to hold on to the rail and also try to get my feet under me. What if I'm walking across the street and a car comes, they don't see me? Am I going to be able to move out of the way? It's going to be harder, right? Even driving, going from one pedal to the other, okay? Those are some practical kind of things. Of course, you can relate this to athletics, right? And we're going to look at a table here in a minute that has some different percentages. Okay. Now we have just the opposite, and essentially the characteristics just flip. This is going to be a more aerobic fiber. Again, it's more on the physiology side, but aerobic is going to be a longer duration, not a sprint. All right, we're going to use oxygen. In the other cases, we're going to use our stored ATP or some anaerobic glycolysis. It's ATPase, not as fast. And we don't need it to be working that fast. We've got time. Calcium, we're not as worried about it being released and being taken up in a timely fashion because our movements are going to be a slower, a longer duration. Again, we're not stopping and starting. We talked about the mitochondria. Again, this is where aerobic metabolism occurs. So we're going to have a bunch of them. Don't need them in fast twitch. Okay? Very few. We're going to use the ATP we have. When it's gone, the fiber is going to be done. Okay? So it doesn't last very long. And the opposite, it's fatigue resistant. As long as you supply it with glucose, glycogen, fat sources, it will continue to contract. Okay? Now, any questions about that? So again, these are going to be, again, pretty much the opposite. We're going to have long duration submaximal exercise. No, we can keep that a little bit longer. Long duration submaximal exercise.
So an activity like this would be just like walking regular?
Yep. Or it could be even as intense as a marathon, right? That's still long duration, submaximal, right? We can't sprint 26.1 miles. Okay? Now, does anybody know what the average pace in the world record marathon is?
6 or 7.
Miles per hour? Wise? how fast they're running? Anybody here run? You don't have to be marathons. You can just run for fun and you know kind of what an average pace is.
I mean, it seems like they're like, are you talking like good runners or?
I said a world record.
Oh, I would say like 5, 6, or 7 minutes.
Under 5.
No, it's under.
Okay? So
Is that guys?
5 miles per hour, or 5-minute miles is how many miles per hour? 12. Okay? They run just over that in terms of miles per hour. It's like 13-ish miles per hour for 26. That's the males. The females is not that far off. Not to think that, oh, they only run. It's not that far different. It's still above 10 miles per hour, right? I mean, but they do that for 26 miles. So if you ever watch it on TV, think about 15 miles per hour, and that's what you're supposed to drive on the boulevard. Okay? You know, with those speed bumps there, 15 miles per hour is how fast you're supposed to go. Think about if you fell out of your car going that fast, how much it would hurt. Okay? Now, how fast does the world's fastest man, and again, woman, it's not that far off, how fast do you think they run for the 100 meters? Low 20s. Okay, that's the average. That's just if you did simple math. It took them 9.8 seconds to cover 100 meters, convert that to miles per hour. The average is around 23 miles per hour. Okay, so they're running a little bit faster, probably at one phase, and then they slow down into the end. Again. That's closer to what people drive on the boulevard. Okay, so again, if somebody falls down, it's going to hurt, right? They trip. They fall, you're going to leave quite a bit of skin on the track, okay, or the road if it's a marathon kind of thing. Okay, let's take a look at a figure that gives you an idea of what percentage people have. So some of them are athletes, non-athletes, just to give you an idea. Okay, so if we look at the top, cross-country skiers. Everybody familiar with cross-country skiing? What's cross-country skiing? This is not alpine skiing. This is not when you go to the top of a hill and you fall down. Okay? That's alpine skiing. That does not require a lot of aerobic activity. That requires a lot of mass. Okay? Physics. Potential energy, bigger rock at the top of the hill gets down faster. Or if you sled. If you go sledding, we haven't had any snow, but big thing gets to bottom of hill faster than little thing. Okay? This is this. You can still go uphill and downhill, but not big uphills and downhills. Much more aerobic. Okay? They have the highest, again, average of about 80% slow twitch. Okay? And you can see the bars there in terms of how far the range from that, up to about 95%, down to in the 60s for slow twitch muscle fibers. Okay? Why is that better? And pretty significantly better, right? Again, this is the end, and this is the average, right? This is the low, and this is the average. Why are they much higher than long-distance runners? Why is there a significant difference? Want me to do the movement again? Correct. I'm using more muscle mass. Okay? If you look at this side, again, this is more of the physiology, but this is our maximal oxygen consumption, or our VO2 max. Okay? So does it make a little more sense? If I'm using more muscle mass, I'm consuming more oxygen versus that runner that's just, right? We don't want to use any oxygen in our arms, right? We want to keep them in place, keep them moving, but to keep our balance, but not much, okay? We're not using as much. So pretty significant in terms of that, and that's one of the differences. In terms of VO2 maxes, we've seen on campus with some of our runners up in the 70s, so these are pretty good. This sample of people and athletes included, it's a decent sample, right? I mean, their VO2s are average about 80 and some higher. If you remember Lance Armstrong, he had one of the highest VO2 maxes that was ever recorded, closer to 90, but also might have had a little bit of help, so pharmaceutical intervention that may have got him there. Okay. Now, flip side of that, here's our 100-meter runner, right? We said that 100-meter runner, that's going to be about 10 seconds. If we go up to the 200, again, it's going to be a little over. Double that, 20 seconds. They've got what percentage? About 50. Okay? Now, we've got a little bigger range with these sprinters. Some of the sprinters are over 60%. Do you think this is a real good sprinter? Probably not the best. Okay? All the way down to about 30% fast, or 30% slow twitch, 70% fast twitch. Okay, so it gives you an idea. And then again, you can read, but we see kind of wrestling about a 50-50, hockey about a 50-50. Most everything's about a 50-50. We get up to canoeing or trained non-athletes, swimming maybe a little higher, but in general, we're about 50-50. Now, why do we not see the ratio of fast twitch to slow twitch with the sprinters that we see here, right? So if we said the maximum was 93%, right? Why don't we see 7% down here? Right, that's just flipping the ratio. So high, this would be 97% or 93% slow twitch, which means down here we would have 7% slow twitch. Why don't we see that?
If you use more slow twitch muscles than just everyday.
Exactly, right? If you had 93% fast twitch, how would you look? How would you perform your movements? Student last semester, I'm holding on to it, said you would look like a squirrel. Okay? Ever see squirrels? Do squirrels just, no, squirrels go, and then what do? They hang out for a little while. They go up the tree. They hang out, they rest. Okay? You would have to move very quickly. Okay? Think about all those characteristics we just talked about. Everything's going fast, fast, fast. But it's just like this sprint. We can only sprint that fast for 10 seconds. Okay, so you're not going to go very far. And again, we would go probably a little bit longer if we had a greater percentage of fast twitch, but you'd have to stop because we're using stored ATP. The stored ATP goes away, you stop. Okay? Example of that, think about if we had you come up to the front and jump as high as you could, how long would it take before you weren't jumping as high as you did on the first try? Not very long, right? Probably a few seconds, right? You'd have that maximal jump, and you'd probably, we're going to talk about this, a principle of the muscle is that when you hit the ground, the next one you might get a good jump because you've stretched the muscle more, and it's going to give you a little bit of a rebound, but you'd stop because your ATP would run out. Okay? So that's why we don't have that ridiculous ratio. We've got about a 50-50, and it's exactly what you said. The activities we do 20 hours out of the day are pretty low intensity, right? Walking around, sitting, right? So it would not be real compatible. Okay, so how many of you believe that you are a slow twitch You would be on the ratio of a greater slow twitch. And then why?
Because I don't exercise a whole lot, I don't have a whole lot.
Okay, so some is training, right? So if you didn't train that way, you're probably not going to have a lot. And genetically, you might not train like that because you don't have that profile. Okay. How many of you think maybe if you participated in sports, you participated in slow twitch sports when you were really a fast twitch athlete or vice versa? You thinking of an example? What kind of example you think about?
I mean, I think that I have more like slow twitch. I don't know, like I'd much rather run long distance than sprint. And
Okay.
like, I play like softball and stuff, and all of that is like, a lot of it is like sprinting.
Okay.
Like it can be slow twitch, but I mean, a lot of your first initial
Most of it's fast twitch, right?
Yeah.
How long does it take to swing a bat? Not very long. How long does it take to run to first base? Not very long. How long does it take to run the outfield? Not very long. Okay? So most of the time you would classify that as a fast twitch type person. Anybody else? Somebody else raise their hand.
I used to do long distance running, and this make me a thrower for some reason.
Okay. Which one were you good at?
Neither, but decent kind of throw.
Neither.
I'm not very athletic. Try.
Well,
Just got a participation trophy.
there's some skill in both of those. It's not just physiology. But anybody else? Again, we've had people who say, like, again, it's maybe a little less obvious in a team sport, more in an individual sport. Like that kind of an idea where I was a long distance runner in cross country and I sucked. But when track season came around, they made me a sprinter and I was great, right? So that they've kind of figured that out with versus somebody like in a soccer or a basketball where when we did the conditioning test, I got crushed. But if we had sprints, I was always first, okay? So sometimes people have figured that out. Anybody else have one?
I was just gonna ask what you thought basketball was, if it was like a slow twitch.
I mean, again, most everything is going to be in that middle, right? Again, you're going to see explosive athletes, right? I mean, I'm sure you see in basketball, men's and women's, right? Those athletes that are explosive. They're quick, they're fast, right? They make moves, they get rebounds, and they're way up there. And then you got people who, and that's why one of the things I always ask, if you were starting a volleyball team, would you want to start it with cross-country skiers? No, right? They have zero or very low fast twitch. Well, jumping, blocking, hitting is fast twitch, right? So you don't want them on your basketball team. They're not going to dunk, right? You're going to see them in a celebrity dunk contest or something, dunking, okay? And vice versa. You probably don't want the sprinters on your triathlon team, right? It just doesn't match their physiology. But in general, they're going to be mixed. I mean, basketball is primarily anaerobic, right? They kind of sprint, sprint, sprint. Now, the rules and some other things have made it, there's always timeouts and fouls and all sorts of nonsense that stops the game. So they don't have to run maybe as long. But if you see basketball go for about 4 or 5 minutes, what is everybody doing? Man. It's because it's all anaerobic, right? And they don't have a great aerobic base. But it's mixed. Again, that's one where it's hard to really tell, again, unless you did like a conditioning test and you saw this person, again, does really well on the conditioning test, but they can't sprint for anything, right? They're not fast, okay? Or they don't jump very well. Okay. Do you have any interest in learning how we learn about muscle fiber typing? Semi-graphic. If you don't like graphic things, you can put your earphones on. But it's kind of interesting. Interested? Yes? No?
Yes.
Okay, yes. Muscle biopsy. Interesting procedure. Most often we're going to take it from the vastus medialis, which is one of the leg muscles. Okay? Why? Relatively big muscle, nerves aren't close, blood vessels aren't close. We don't want to damage those when we're taking out the muscle tissue. Okay, so what do? Numb up the skin. That's where the pain receptors are. Once we get past the skin, it's just pressure, right? Not real pain. Okay? Small cut. Not a big cut, pretty small cut. Okay? We've got to cut through the muscle, any fat, right, that's on top of the muscle, or cut through the skin to get down to the muscle, get into the muscle, so we can sample inside the muscle, right? Now, we take a needle. Needle's about this big, okay, in terms of diameter. We put that into the hole. We have a suction that at the bottom of it has a hole in it. We have a plunger. We suck the muscle into the tissue, the muscle tissue into the needle. Okay. There's another plunger that's sort of inside that has a blade on the end. You take that, you slam that down, cuts a little piece of muscle, about as big as a eraser head. Okay. Then we glue it onto a mount and we slice it up. Okay. Then we give it different things, like if there are different ways that you can identify muscle fiber typing, but essentially we stain it. If it stains one color, a lighter or a darker, it's fast twitch or slow twitch. We can also identify a few other things. So that's how we do that. Okay. Kind of interesting. When I was in graduate school, we could volunteer to do that. And the professors just bought a kit and just went in the lab. Obviously, we cleaned it up. I didn't mention this, so we clean it. And the professor would just do it on somebody, okay? One of the students. And then we'd give it to the person who ran the lab, and they'd run through and see what your profile was. So I volunteered, but I did not do it, okay? It's not really, I'm not great with that kind of stuff, but I tried. At least I volunteered. Somebody else did it. So that was at the University of Tennessee when I was doing a master's. When I got to West Virginia, in the state of West Virginia, only physicians can do biopsies, muscle biopsies. Okay? So we had a professor who ended up being the department chair after a couple of years, but that's all he had done is muscle biopsies. And he'd done thousands of them on people. Okay? That was his research. Well, he had to teach somebody, and ended up being a neurologist, to do it. So she had to practice on non-humans prior to, right? I mean, there's that kind of thing. And then she did some of them. So a project that I worked on, she was responsible for that. So just kind of interesting, some of the laws. What happened to his research focus? Animals, right? Because it's hard for a full-time working physician to do biopsies whenever he needed to do them. So he ended up moving over to animal research. What happens when you do animal research? And this is what I did. We trained rats. So we had them run on a treadmill to see what happened to their aerobic system. My specific interest was in the enzymes that are responsible for aerobic metabolism, one particular that we looked at, somebody else. But at the end of those studies, we don't just take the biopsy, we take the entire muscle. Okay? So the animal is euthanized, okay, using carbon dioxide to knock it out, and then there's a guillotine type device that removes the head. Okay? And then we had to pull back the skin and remove the muscle. I was looking at the soleus muscle. So took the soleus, somebody took the heart, somebody took other pieces of the body. Okay? So just kind of gives you an idea in terms of exercise science. We use lots of models. Why can't we use humans? Well, we can't do that, right? We can't obviously kill the person and take out their entire muscle. But people also do not volunteer to give up muscle biopsies often either. And the physiology of the rat is very close. Okay? So a lot of the training is used for animals. They also had, connected to the university was NIOSH, which is National Institute of Occupational Safety and Health. You might have heard of that before. Occupational Safety and Health. They set regulations for safety and health in the workplace. So they did research on like repetitive movement research. So what happens if you are at a job where you do the same thing over and over and over again? What happens? But they developed a leg press for the rat. So you could actually do resistance training for the rat. So it was a nose poke, so they pushed their nose up through, and they'd have to do so many reps, and then the food would come out, so they could eat. Okay? So exercise science has lots of different areas. I'm not interested in those areas. I did it, and I learned about it, but what's the difference between a rat and a person in terms of training? Well, how did we train the rat? We put the rat on the treadmill, and we turned it on, and we sped it up. Now, rats like to run. If you're not familiar with that, that's what they do, right? They run. So they're happy to run. The rats we had were a strain that were fat rats. So they didn't necessarily like to run, okay? They were obese, okay? And again, hence we were looking at the different tissues and seeing what was happening. So what happens when a rat doesn't run on the treadmill? No, it's inside a box. So it cannot fall off. What's at the back of the treadmill? Yeah. So little electrodes, two elements, one foot, another foot, touch, little shock. Okay? What happens when you're a real fat rat? We just talked about insulation, right? You just sit down and you don't get the shock. Okay? So then we would just have to give them a little bit of a nudge with a pencil or something. And again, that wasn't something that's really big. But we obviously can't do that to people, right? So we would say they're going to run, the rats, we were going to say they're going to run 30 minutes at this intensity of this grade and see what the adaptation was to the physiology. That's very easy to do, right? And they would do that. We can't do that to a person, right? A person says, nope, I'm not interested, okay? There's something called informed consent. Person signs up for research, they decide they don't want to do it, they go home, okay? That's a challenge with human research, because if I spent 2 months training you and then you decide you don't want to show up for the last testing session, I have nothing for data, okay? So they're necessary evils of both. I'm just more on the applied side, because we know what to do physiologically to design programs for people. We need people to do them, okay? So that's why I wasn't that interested in animal research. Okay? Any questions about that? Pretty interesting. You can find videos online from exercise where the person has a hole in their leg, they're pedaling a bicycle, they briefly stop, they do what we said, and they cover it back up, and they continue to pedal, and they do it again, and they continue to pedal and do it again, to see what happens with fatigue, supplementation. So if I'm giving a certain amount of glucose to them or different types, and they're pedaling for 30 minutes or an hour or whatever, and every 30 minutes they're popping a biopsy out. So there's some other things out there that you can find related to exercise and muscle tissue.
Wait, how do they numb their leg while they're
They just give them enough numbing for it not to wear off. They're just numbing the skin.
Is it sort of similar to a breast tissue biopsy? Like the device?
I'm not sure what that looks like, but I think that tissue is much softer, so you don't need as much of the force. Literally, you're slamming it down, the plunger down, to make sure you cut it. Yeah. So I would say probably not. there's still probably some sort of vacuum and then something that cuts. So probably similar but different. I mean, there's obviously a cutting device and something you're sampling from, but different. Any other questions? There's one more thing I was going to say. I was going to say, at Ball State, they work with both their cross-country team and their swimming team, and they take fairly regularly biopsies to evaluate their training. So the runners will come in and they'll do biopsies, and then they do it in the shoulder, more in the lat, for the swimmers to see what the training has done to the physiology. So there are athletes who do that fairly regular basis. You probably wouldn't get me again to sign up for that, but
That just becomes like scar tissue, doesn't it? Like where you take out.
yeah, you just use strips to close it up. So it's not a lot of damage to the muscle. It's a very small portion of the muscle that you're taking out. So there's not a long-term effect, but yeah, it would just heal over. Okay, so we've got a few minutes left. Let's look at the blood supply. So we've talked a little bit, and it's kind of a transition with the last slide, looking at a VO2 max, and we said we've got to have oxygen there, and we also talked about the electrochemical action potential. We've got other systems that are involved to get the muscle to contract. So we definitely need the vascular system. So the blood supply is going to come via arterioles and capillaries. Capillaries bring the structure in which the oxygen is exchanged with the tissue. It's going to leave via the smallest on the venous side, the venules. And this is in and around the endomysium. Okay? So again, that most interconnective tissue of the muscle. What is it bringing? It's going to bring nutrients. It's going to bring oxygen. We can use glucose from the vascular system, or we again have that storage form. We talked about glycogen. What's it going to remove? Heat and carbon dioxide. And you're probably familiar with that, right? Our temperature elevates when we exercise, right? And we sweat to cool ourselves off so we don't overheat. We're really inefficient, right? We produce a lot of heat compared to the amount of energy we get out of that. If you remember from metabolism, when we break everything down, whatever it is, we end up with CO2 and water, okay, from metabolic processes. So the result's going to be CO2. Obviously, that's not real great for us, so we're going to remove that, exhale that out. Okay. Now, one of the pretty cool parts is, in terms of the physiology, those capillary beds that are in the muscles, we don't use them all the time. Okay? Again, we talked about earlier, some of your muscles are working, some of them aren't. Do we need to be sending a lot of blood to the muscles that aren't working? No. So what do is we close those off. And when we need them, then we open them back up. And that's dilation. Anybody cycle or ride a bike? What do y'all do? Nobody runs, nobody cycles, y'all fish? Y'all lift weights? What? Nothing? Okay. How I think of this is, if you ride a bike, and you might feel it with resistance training too, but it seems I've noticed it more. When you ride a bike, how do your legs feel when you get off? Well, they feel twice as big as when you got on, right? Why? Because all the blood went there, right? Did I need blood up in my arms? No, I'm just sitting there, right? I'm just holding on to the handles. So I don't need oxygen to be coming out of there. I don't need blood up there. So all the capillaries in my legs have opened up, and that'll give us more capacity for blood, more capacity than for oxygen exchange. Okay? But we don't need that now, right? Now, in terms of exercise, what happens? What effect does exercise have on the delivery of the blood and the oxygen? Well, when we have rhythmic exercise, something where it's continuous, right? We're jogging, we're swimming, we're cycling. It's a repetitive motion, rhythmic. And it's also got some kind of cadence. That's where the rhythmic comes in. When the contraction occurs, the flow is reduced. When the relaxation occurs, the flow increases. And we call that the muscle pump or milking action. Okay? This muscle pump is not when you lift and your muscles get pumped up. Okay? Same idea as we were just talking about, except now we're trying to heal the muscle. We send in elements to try to repair the muscle. But as the muscle contracts, it cuts off flow. As it relaxes, it opens it up. And again, it makes sense in a rhythmic exercise, right? When I'm pedaling, when I push the pedal, right? That's when the muscle's contracting. When I bring it back up to here, that's when it's relaxed, right? So it's over and over. Contract, relax, contract, relax. Okay. Now, I just mentioned riding a bike. Right? Where's the practicality of this come in? Riding a bike, right? Say I've ridden a bike for an hour, right? Where's all the blood? You said, in our legs, right? Good idea to just stop and get off the bike? Why not? What's likely to happen?
You get lightheaded?
Timber, right? No more milking action, right? Here, muscles contracting, relaxing. It's pushing the blood up. I do this. Is that happening anymore? Blood is here. Gravity is doing this, right? Keeping it down there. If I don't have this pump squeezing the blood back up to the heart, it does not get to the brain. If it does not get to the brain, we fall down. What happens when we fall down? Now we're horizontal, and it's very easy for the blood to go from our legs. Not very easy, but it's easier for our blood to go from our legs to the pump to get back to us. Okay? So that's the reason why we do cool downs. Okay? That's the practicality of this. That's why you do a cool down. You do some exercise, you gradually re-equilibrate the blood so that it's getting back to the pump. So it's getting back to the skull. Now, any other situations where people pass out? Anybody passed out before? What sort of reasons?
I got overheated, so I passed out.
Overheated? How would that be affected in this?
Working too hard, maybe?
If I'm overheated, I'm probably dehydrating, right? If I'm dehydrating, it's harder to get that blood back up to the pump because it's thicker, right? You need a greater pressure. Doesn't get back to the heart, doesn't get to the brain. What else? Anybody else?
Not enough airflow.
Okay. From like what?
It's actually on the last screen, so I thought I had pneumonia.
Okay.
There were like a class members who do burpees. They go over very well.
Okay.
I thought I had some.
Pneumonia and burpees probably doesn't go over too well. Probably not the same thing as this, but something. Okay, I'm just going to finish up quickly. We're a minute over. When else does this happen? Well, it happens at weddings. Why do people pass out at weddings? Okay, we have several reasons, and they all come together. I heard locking out legs. What happens when I lock my legs? Muscles are contracting, reducing flow. I heard alcohol. Alcohol is a dehydrator. Now I have thicker blood that I'm trying to push through there. It's often in the summertime where it's hot out. Plus, we didn't have anybody share, but people pass out because of nerves, right? People get nervous and they pass out. So when you put all those factors together, it's a good chance somebody could fall down. The other time that this can occur is military, right? Again, similar kinds of situation. If they're at an attention position for a while in the hot sun, blood didn't get back up to the heart, you see them pass out. Okay, so those are kind of the practical applications of what's happening with the blood flow and getting it to a point where, again, it's back up to the pump. Okay, quiz Thursday. See you then. So it's not really specific to swimming, maybe because there's a greater risk. I thought you were going to say like you were swimming in the river or something and somebody had to rescue you, or you just got thrown. They just tossed you back and forth. Does that make sense though? So that's where this comes in, is we can shuttle it to where we need it. Main areas, again, we've got to keep the brain going, otherwise we can't have the muscular contractions. Again, that's what happens if we run out of fuel, right? If we run out of glucose and we don't have enough fuel to fuel the brain, people that were running, they start to do this, right? They can't coordinate themselves anymore. That's from here. That's not from their muscles having fatigue. You just don't have enough fuel to run the brain. And again, you don't listen to the brain will turn off and you'll listen. So what do we have in terms of athletes or the capabilities to train this for an aerobic setting? Untrained person is going to have 1 to 4. Aerobically trained, we can get a few more, right? And that's, if you saw in the figure, it had capillaries, I think, around it, but they're just surrounding the fiber. And again, that when we talked about the biopsy and how you would stain, we just stain for a protein in the capillary, and we literally just count the 4 or 5 little dots around the fiber. Resistance training, kind of in the middle. Again, resistance training is an anaerobic activity. We don't need capillaries. Okay? We're using stored ATP or high levels of anaerobic metabolism. This is for aerobic metabolism. We don't see as many, right? Half as many as the aerobic. We still have some, right? But we don't need them. Any questions with that part? All right, this is where I was talking about where we can actually shut off the blood flow. And that could lead to, again, passing out. And we usually talk about Valsalva. Okay. Let's talk a little bit about vascular physiology. Which set of vessels are under high pressure? The arterial side or the venous side? The arterial side. What does that mean? That means we do not want to mess with them. Because what happens if we were to perforate an artery? The blood is going to come out fast. Any idea how fast? Well, usually we have about 5 liters or so of blood. Again, depending on person size, but kind of an average. And our cardiac output, the amount of blood we pump per minute, is about 5 liters. Okay? So if you get a big hole in an artery, you better seal it up pretty fast. Okay? Otherwise, the blood will, if it's inside, will be inside of you. If it's exposed to the outside, it will be on the ground. Okay? So you got about a minute. Again, we've seen this with athletes. There have been some hockey players who've come really close, getting a skate in the neck, and blood being everywhere, squirting. And that's, again, I'd say at rest, 5 liters per minute. Maximal exercise, again, depending on size, we can go up to 30, 40 liters per minute. Okay? So that's even less time to be able to do that. But the other part of this is that the venous side is not under pressure. Okay? And that was part of why we have to pump the blood back up. Right? It gets down to the muscle. How does it get back up? There's very little pressure. So we have to use the muscle pump. Right? And again, we said if we don't use the muscle pump, then we stop until the blood gets there. Okay? Why? How does the blood get, or what's different about the venous side versus the arterial side in kind of the structure? What's different? Why doesn't the blood just go all the way down to my toes if I'm here and I'm obviously not contracting, relaxing to get the blood back up? Why isn't it down in my toes?
You have valves.
Valves, right? What do the valves do? Well, if there's enough pressure, opens the valve, blood goes up. If there's not, it closes. Okay? What's the condition where those valves are damaged? Varicose veins, right? What happens? This one's damaged. It just lets blood go anywhere. The next one catches it. It swells, right? That's where it is. How do you know you have valves in your veins? If you've got good veins, take one of them, draw it back to your heart, watch it flatten out because there's no blood going through it, and then release. Y'all got veins? What's wrong with y'all? Oh, you got great veins. Pressure. Draw back to, no, you got to hold the pressure. Draw back to your heart. No blood coming up until here. Right? You got to hold here and then draw back. See how it flattens out?
Yeah.
Then when you release, it comes back up. Okay? That's just a way to remember you have valves. Okay, now, how much does it take to close it off? I think about this like a garden hose, right? How much water you have to water the yard, right? If I don't have any sort of device on the end of the hose, how do I make more force? Right? Got to make it small, right? So I'll squeeze it a little bit, right? That narrows the diameter, and that creates a greater pressure as it comes out. What happens if I put a kink in the hose? Almost will shut it off, right? Depends on how good a hose it is or whatever. But if I put that kink in it, very little water will get through. So same kind of an idea. When we squeeze down on the muscle with 60% or higher of our muscle mass, no blood gets through. Okay? And again, a max squat or a maximal lift with a lot of muscle mass is obviously much greater than 60%. So I've shut off the blood to the muscles. We said if we held our breath, we were shutting off the blood coming up to the heart, right in the torso with pressure. That's how we pass out. Okay, so really not that much, right? 60% of your max, we can stop the blood flow. And again, that's why we breathe. And again, usually it's a cyclical pattern where we'll contract and we'll relax, and we can maintain the blood pressure so that the blood continues to flow. Okay. Why is that not a challenge? Is because, again, it's not an aerobic event. We're using the stored ATP, anaerobic glycolysis. We don't need oxygen. We don't need the blood flow. To do the work. But we can't shut it off because it has to get back to the pump. Any questions with this part? Again, just trying to include some application, again, of things that people will do, why they might pass out. And obviously, you want to teach them not to do that. Okay. Any questions with this part?